I'd like to say something about layout and other things to do with the syntax of Haskell in this segment. When you make a definition in Haskell, like mystery x equals x multiplied by x, how do you know when the end of that definition is? The answer is you don't know until you hit something that is offside with respect to that definition. So a bit like the rule in football and soccer, the beginning of the right hand side of that definition doesn't have an explicit end. It's only ended by something being offside. The next definition here appearing in that first column makes the definition end. I mean, alternatively, in most languages, you just have a thing like a semicolon that says, here's the end of the definition. And indeed, you can do that in Haskell, but you just don't have to. And the tradition, nearly everybody uses layout as a way of showing that they've reached the end of that part of the definition. Now, the rules for layout can be a bit complex, but the great thing is that your editor will help you out. Editors will typically support a standard style for layout, and that's the layout that makes the most sense, and it will usually do the right thing. And we'll see that when we jump into the editor in a second. We'll see that in action. Just before that, I wanted to say something else about naming functions and constants. I think perhaps it's been obvious that when we've written definitions in Haskell, we've begun the identifiers, the names of the functions, with a small letter. And that's because names that begin with a capital letter are used for type-related things. Names of types, names of constructors for types, and so on. So it's not been accidental that we've only used identifiers that begin with a small letter. There's also some words that we can't use as names for functions. I've listed those. Those are what are called reserved words. And there are some names called special identifiers that mean something in some particular situations. So it would be, I think, it would be unwise to start using those as definitions of functions. You can do it, but I would not advise doing that. Let's jump into the editor now and look at some more things to do with the syntax of the language. Okay, here we are. One thing that you can see here is that I have defined something which doesn't have where the identifier looks very odd. It's a user-defined operator. And I've done that by enclosing the operator in parentheses and giving its type, and then in lines 37 to 39 I'm defining that operator, and you can see it's actually a new version. It's a version of the max operator for over integers, so we can write our own. On the other hand, we can always make a function infix by sticking it in back quotes. And my personal feeling is that it's often easier to interpret the name of a function from its name, which hopefully means something, rather than from the choice of symbols you used for an infix operator. So I tend not to define my own infix operators, but I know people do, and there are a number of standard ones that we'll find out as we go through the course. I thought it's also worth just showing you an example here of defining the mystery function. Mystery of x equals, I don't know, x times x. And then we think that's not the end of it. It can plus 4. We can go plus x. And it's only when we go to, we have another definition that we have, that we end the definition of mystery. And you will see here, if we reload this file, we'll see that mystery does what it should do. If we apply it to 4, we get 16, 20, 24, I hope. Oh, now here we're seeing an error message that it's worth noting. Why have I got an error message? The answer is I didn't save the file on the left. So if I save it, go back into the editor. Oh, sorry. Save it, go back into the editor, reload, and then type mystery of 4. I get the answer 24. So when you get a message variable not in scope, it's perhaps because you have defined something in the file, but you've not saved it before you reload it. Okay, that's what I wanted to say about layout. And the final thing I wanted to talk about was if we write expressions like using operators like minus, we write something like 2 minus 3 minus 4. It's not quite clear what that means. It could mean subtract 3 from 2 and then subtract 4 from the result, or it could mean subtract 3 minus 4 minus 1 from 2. But the answer is, the way that it is interpreted in Haskell is that it is left associative. We get the same result as if we bracket it to the left. Now, some things it doesn't matter. If we write 2 plus 3 plus 4, it doesn't matter how we bracket it. But if we write 2 plus 3 times 4, that could be 2 plus 3, 5 times 4 is 20, or it could be 2 plus 3 times 4, which is 14. And the answer is it's 14. And that's because multiplication has a higher binding power. If you like, it's stickier. It grabs the 3 and the 4 harder than the plus grabs the 2 and the 3. And if you look in the appendix C of the book, you'll see a lot of detail about the associativity, how you bracket when you have 2 occurrences of an operator like 2 minus 3 minus 4, and also binding power. So how you disambiguate when you've got 2 operators and you could bracket things in 2 different ways. But the answer here, as always, is to make sure, if in doubt, to include brackets. So if you want it to be 2, if you're not sure whether it's going to be 2 plus 3 times 4, putting a bracket in doesn't do you any harm. And if you do actually want it to be 2 plus 3 times 4, putting those brackets in will make that happen. So, as I said in a previous segment, languages make choices to try and make things a bit easier to read, so we don't have to write parentheses all the time. There's this notion of binding power. But sometimes, if you just are not sure what the binding powers are, then putting the brackets in will sort things out for you perfectly happily. That's what I wanted to say about a few syntactic details like that, particularly about the way that operators work. So that's it on syntax.